Professor Vikram Rana. He'll be talking about X-ray properties of cataclysmic variables.
Okay, so I'll be talking about the X-ray study of cataclysmic variables. These are another type of X-ray binary systems. In the morning, which will give a nice overview of the X-ray binary systems and different physical processes happening in the system. So these are type of binary systems. The projects that I have been involved basically are, of course, the study of cataclysmic variables through the X-ray eye and ultraluminous X-ray sources, and of course, a couple of other experimental projects that I have been involved. So today I will be mostly talking about CVs, the cataclysmic variables, which the work which I have done with my PhD student Anirban Dutt, and ULXs I have been working with Tanuman Ghosh and Aman Upadhyay. So I think I will skip the ULXs for today, and we'll go to the CVs and some of the experimental project apart from the POLIX that Vishwit has mentioned in the morning. Okay, so what are these kind of variables? These are again very interesting binary systems, and in the morning, as Vishwit mentioned, that there are two stars. One is a compact object, one is a secondary star, and the accretion material is coming from one star to another star, and they are moving around their common center of mass. So here, if you replace that neutron star with white dwarf, another compact object, then it forms a cataclysmic variable star. Okay. Now these stars are pretty interesting, as the name suggests. Earlier, when people used to observe the stars, they have undergone a lot of catastrophic events, and that's why they call it cataclysmic. And these are highly variable stars, so they vary on the period of minutes to hours or days also, and weeks also. So there is a wide variety of the stars that undergo these kind of variations, and the X-rays, as usual, are produced via accretion process. So there is a white dwarf, there is a late type main sequence star, and the material, when it overflows its Roche-lobe, the material flows from the secondary star to the primary, and to conserve the angular momentum, it forms an accretion disk, and that's how the X-ray gets produced. So simple picture looks something like this, and these are the most main component, basically the companion star, the primary star, and the white dwarf is also spinning around its spin axis, and in some cases white dwarf may also have the magnetic field. So then the magnetic axis will be not necessarily aligned with the spin axis, and we might see some periodicity as a function of that, and there is an accretion stream and there is an accretion disk. So these are the main ingredients or the main parts of these systems. Now there are a variety of systems, as I told you. In some cases the white dwarf may contain magnetic field, in some cases it may not be. So there have been several classifications or division. Sorry. The orbital period is basically how long it takes for stars to complete one orbit around their common center of mass.
Oh, for the pair.
For the pair, correct. Yes. So yeah, so that's actually a good question that reminded me that this is a very distinctive property, because here this object, this entire system is very compact. So it takes only few hours for them to complete one orbit. Unlike in the morning when we said might take days or sometimes weeks also.
So what's the typical distance between the pair? I mean the two members.
So basically we can calculate. It's basically just a few hours. But in common words, if I say that you can fit nicely this entire system into sun. So it's basically kind of diameter of sun.
Force which must be acting on the matter is also like going to be enormous, right?
Yes, correct. So basically fast in the sense that the distance between them is smaller. That's why they take less time. So speed wise, actually it's not that fast, so that it will kind of catastrophically.
I'm just trying to see whether compared to the gravitational forces which is holding each of these objects, how big are the centrifugal forces?
See here, basically this is
to tear it apart. No,
I don't think so, because this is actually one solar mass white dwarf. Okay, and it's basically scaled down version of the neutron star, Neutron star has roughly 10 kilometer of radius. This is 1,000 times more, so it's 10,000. So the density is not that high. So I don't think it will. Okay, so these are basically different classifications, and one of the important parameter to classify these sources is the magnetic field of the white dwarf. So what people did is that they estimate the magnetic field of the white dwarf, and based on that, it turned out that this CVs can have magnetic field anywhere ranging from 1,000 Gauss all the way to the mega Gauss or tens of mega Gauss. Now, of course, these numbers are pretty scaled down compared to neutron stars, pulsars, or magnetars, which have 10 to the power 12 Gauss or 10 to the power 13 Gauss magnetic field. But so if the strength of the magnetic field for the white dwarf is of the order of 1,000 Gauss or 10,000 Gauss, then for practical purposes they are considered as a non-magnetic, even though it has a magnetic field. But the role of the magnetic field in accretion is very insignificant compared to other sources, other classes, which are called polars or intermediate polars, basically the magnetic CVs, where the magnetic field is of the order of million Gauss or tens of million Gauss. It's called polar, and intermediate polars they are basically between these two systems. So where the magnetic field is of the order of 10 to the power 5 or 10 to the power 6 Gausses. Now this actually is very important parameter, because this is what defines the geometry of the system. If there is a very strong magnetic field of the order of a million Gauss or tens of million Gauss, then because of the compactness of the system, the magnetic field can extend all the way up to the inner Lagrangian point. So as soon as the material leaves the secondary star, the magnetic field will start acting on it. Okay, and because of that, there is no room for formation of the accretion disk. So these systems, basically you won't see any signature of the accretion disk, or other words, I would say that there is no reservoir of the matter in these systems. Whereas if you go to the intermediate polars, which are in between these two sources, there is some room of formation of the accretion disk because the magnetic field is not strong. So it will allow some partial, or I would say truncated formation of the accretion disk. And at some point, when the magnetic field becomes strong enough, it will take over the material, and the material will follow the magnetic field lines and falls onto the poles of the magnet on the white dwarf. So these are the broad classification for the CVs, these binaries, that for non-magnetic CVs, as it is evident that the magnetic field doesn't play much role, so there is a full accretion disk instead of partial or truncated accretion disk, or in this case there is no accretion disk. So the accretion disk can extend all the way up to the surface of the white dwarf, and that is the reason which produces the X-rays. Yes, we can, but not as fast as neutron star. There is a spin period of the white dwarf, because this is ultimately it's the same phenomena. The only thing is that it is rotating slowly. So we do see that pulsation. Yeah. Huh.
So fairly regular. I mean, there's an orbital period, there's an accretion disk or no accretion disk, magnetics. So what is the cataclysmic aspect of this?
Correct. Basically, this is kind of historical, that earlier when this large chunk of the CVs are basically nova systems. So these nova expansions, they regularly go into the outburst, and for example, if this is a dwarf nova, their regular outburst has been observed. So like few weeks or few months, they will be once in a while go to the outburst. So initially, this class of systems were actually discovered by these systems. So the name came from cataclysmic variables.
Vikram, maybe I missed it. You said means such high magnetic field like million Gauss or hundreds of million Gauss means what is the origin? Because in lab, imagining such field is very difficult, right?
Correct. I think currently, I mean, theoretically, it is still kind of open questions that how this magnetic field comes, but it is kind of hypothesized that the white dwarf will born with such kind of magnetic fields. Now, you said that this is such a high magnetic field, but as I told you, compared to pulsars or magnetars, this is much less, which is 10 to the power 12 or 10 to the power 13 Gauss. So compared to that, this is still kind of quite less. Yes, I think once that magnetic field is there, it is kind of difficult to disrupt that, and it stays there for till forever. Yeah. Okay, so if you look at the artist, view of these systems, basically, so as I told you earlier, you can imagine this is a kind of secondary star which is overflowing its Roche lobe, and the accretion stream interacts with the accretion disk and slowly falls around. Now, at some point, basically, it will interact with a magnetic field, where the magnetic field becomes strong enough. So here you can see that the material actually follows the magnetic field lines and falls on the white dwarf surface. So then it creates a kind of accretion curtain around the white dwarf systems, and this actually acts as one of the absorbing parameter, that when the X-rays are emitted through white dwarf, it is all surrounded by the accretion curtain, especially in these systems, the intermediate polars, and that produces complicated absorption effects. Whereas polars are relatively kind of clean, clean systems, where you don't have accretion streams, so they directly follow the magnetic field lines. So the consequence of this is that, as I told you, that you will see some signature of accretion disk here, unlike polars where there is no accretion disk. And this magnetic field, actually, because it goes all the way up to the secondary star, it tidally locks both the system. Okay, so just like Earth-Moon system, it will always see the same phases, and that means that the rotation of the white dwarf and the orbital period of the two stars are same. Okay, so we don't see any multiple periods in this system. When we try to look for the periodicity in the system, there is only one period. Whether you call it a spin period or the orbital period, it's the same. So the magnetic field actually plays a very important role here. Whereas in this system, where the magnetic field is not so strong, it actually allows the white dwarf to spin at different rate compared to the orbital spin. So when you try to look for the periodicity in the light curve of the system, you will actually see at least two periods. One is spin and one is the orbital period. So that is another observational difference between the two systems. Okay, and observationally, it has also been seen that this IPs are mostly dominant in hard X-rays, basically about 10 keV or so, and polars are mostly observed in the soft X-rays. Now, one of the consequence of not having the accretion disk is that, as I told you, that accretion disk basically acts as a reservoir of the material. Okay, so let's say if some event happens catastrophic because of some reason, if the accretion stops temporarily, okay, then there is no reservoir of the material in this system, so the X-ray emission production also stops. So this systems has been shown so many times going on and off stage in X-rays, okay, because there is no mechanism for producing the X-rays. Whereas here, even if the accretion stops, there is still material to produce the X-ray for some time. Okay, so if there is inhomogeneous accretions or the material is, because of some explosion or events, if it has been disrupted, you will see the effect of this in the systems immediately.
Sir, could you explain why one has dominant hard X-ray emission and the other one has soft? Because I was expecting if it has an accretion disk, it would be emitting in soft X-rays.
No, accretion disk will be emitting in soft X-rays, but the white dwarf, actually, the main component, that is emitting in the hard X-rays. Okay, so here you will see basically the hard X-ray emission. It's just observational property that when you observe both of these systems, it so happens that in hard X-rays the spectrum, the spectrum of this are more flatter compared to the spectrum of the polar.
And in case of polars, why do we expect soft X-ray spectrum?
That is again because the polars, actually I will show you in the next slide when we go close to the white dwarf, which is the region emitting the X-rays. Okay, so there are multiple X-rays, multiple components which are emitting from that region. So I will show you in the next slide why it is there.
If it's disrupted fully,
So if it is disrupted fully, then it's basically distorted system. But
sometimes some perturbations.
some temporary perturbations or some inhomogeneous accretion, that could be possible. Yeah. Correct. See, this is kind of not very strict thing. It is that when you observe, see earlier, sorry, when we were observing these systems, they were mostly observed by this XMM or Chandra, which goes only up to 10 kV. The definition of soft and hard basically is kind of overlapping. So what happens is that then when you look at the spectrum of the polars, you will see a very dominant soft X-ray component, which is basically the disk black body component or the coming, yeah, mostly the disk black body component. So that component is very soft compared to the other power law component or the Bremsstrahlung component. That is what is called the dominant. It's basically relative definition. That's it. Sorry? No, there is no disk in the polar. It's just the accretion column on the white dwarf. Yeah. Okay, so with this observational properties, one of the standard model of the magnetic CVs is that, I think I will go the next slide. Why it is. Okay, somehow it is rotated. I don't know why. Maybe then I will explain it here basically. So, okay. So if you come very close to the white dwarf, what happens is that, as I showed you, that this magnetic field will take over, and the magnetic material will follow this magnetic field lines. So when it comes very close to the white dwarf surface, so this is the white dwarf surface. Standard theoretical expectation is that these are the magnetic field lines, let's say. So the matter is coming and following the magnetic field lines and falling on the white dwarf surface. Okay. So as the material comes closer and closer, the gravitational pull of the white dwarf actually makes them very supersonic. Velocities are very high. So here it's basically the cool supersonic accretion flow is going on. What happens is that as soon as the flow comes very close to the white dwarf where there is atmosphere, it encounters a sudden jump in the velocity. Because of that, it produces a shock here near the surface of the white dwarf, and it is this region which gets heated to the temperatures which is responsible for the hard X-ray emission. Okay, so this is temperature here of the order of 10 power 8 Kelvin, which can produce X-rays of a few tens of kilo electron volt. And then what happens is that slowly that material, after which we call a post-shock region, material tries to settle on the surface of the white dwarf, and the temperature slowly reduces. So there is a strong temperature gradient from here to here, and there is inverse gradient of the density from here to here. So here there is a larger density compared to here. Okay, so there are these two gradients, and this is the area which is kind of very interesting for the X-ray as far as the X-rays are concerned, because all the X-rays are mostly coming from here. So if we assume ideal scenario where the shock is emitting hard X-rays, and let's say the X-rays are emitting in all 4 bidirection symmetrically everywhere, then it is possible that half of that hard X-rays will be encountered by the surface of the white dwarf, which is relatively cool. So then it will get reprocessed and emit either as a soft X-rays or the UV. Okay, so that is where the soft X-rays or the UV component comes from. And this is where also we see some kind of reflection, because it's a reprocessed hard X-ray emission. We do see, expected to see a signature of the reflection. And here, as I told you, there is a strong gradient for the temperature from high to low. If you divide this region into different zones, then it will be emitting at different temperatures. Okay, so ideally, if you want to model the spectra from this region, you actually have to have a multi-temperature model. Okay, and the dominant cooling mechanism over here is the Bremsstrahlung. So the sorry, temperature. Temperature actually it's not quite steady. Here the shock temperature is the highest, and here it's the lowest temperature. So.
And the highest and the lowest, no, I'm saying the highest and the lowest point. It almost looked like that figure I showed where one side you put it in fire and this thing, right? So I'm saying, is it a steady state like this temperature profile? If I look
as long as it continues the accretion, it forms the shock, it will remain at similar temperatures.
Okay.
So that is there, always there. Once if the accretion get disturbed, if there is no shock, then there is no X-rays. This is what is called the accretion column. The accretion disk will be somewhere here, around the white dwarf. In terms of polar, there is no accretion disk. In terms of intermediate polar, it will be somewhere here.
So is there some sudden change in density or something there?
Sudden change in the velocity.
Why that happens?
Because what happens, as I told you, this is a cool shock which is coming with a supersonic velocity. Because the material is actually experiencing the gravitational pull of the white dwarf. So they are following the magnetic field lines, and as soon they come very close to the white dwarf, they will actually encounter with the atmosphere. Because of that, there is a sudden change in the velocity, and that is what generates the shock. Correct.
From the shock downwards, you see in all, according to the temperature, you see it in
Yes.
all frequencies, is it?
Yes. So, yes. Basically, if we have some instrument which is kind of sensitive to different temperatures, now what happens is that this different zones of the temperature will have their characteristics emission lines. Okay. So, if you have an instrument which has a pretty good energy resolution and can resolve the emission lines, you can actually see the different emission lines coming from the different zones, and based on their characteristics temperature, we can estimate what is the temperature of here as well as different zones. Okay. So it all depends on the sensitivity of the instrument. But yeah, it's mostly in the hydrogen burning. The outer shell is mostly hydrogen burning shell. There are some, I think, CO also, but that's very late. In X-rays, actually, we don't see the hydrogen line. That will be mostly coming in the lower part. The continuum is there. So the characteristics lines will be actually, so here when we have this highest temperature, okay, and if you go down, the characteristics lines will again fall in the X-ray regimes. Basically, it's a highly ionized oxygen, silicon, magnesium, sulfur, those kind of lines. Sorry? From the secondary star. Yeah. So if you have that, that's what I'm saying. If you have an instrument which can resolve this emission lines from different elements like magnesium, silicon, sulfur, these are highly ionized lines. Okay. So then you can actually see that spectrum.
But those instruments exist now, so
Sorry?
those instruments are there. So,
No, we have actually some of the grating instruments which it has to work in the X-ray energy range. Okay, so there are some gratings like XMM Newton or Chandra. They have the grating. They can resolve these lines. So that's what I will. When I show you the spectrum, we have seen those lines in the grating spectra.
why I said is because we have some X-ray detectors in our lab. They're very small actually. They're not big. I mean, only this size.
Okay.
That's it.
So here also, basically, when you use this gratings, what I told you about in XMM or Chandra, they are also small. It's a grating only, but you need to have the capability to resolve those lines. That's the only criteria here. Okay, so we are when we look at these sources. So this is all theoretically expected model that when we look at these sources through X-ray eye, what are the different components we are supposed to see? Okay, so this is hard X-ray emission. Then this is a reprocessed soft X-ray emission or UV emission, and different emission lines from the regions. So this is the important region as far as the X-rays are concerned, and we can see very close to the white dwarf. Okay, so then I think I will kind of skip this one. It's more or less similar thing that I am showing here. Okay, so when you look at the spectrum of the sources in X-rays, then the ingredient of this spectrum, if you can somehow observe this starting from sub keV to few tens of keV, okay, so then you will see this kind of spectrum here. This is the overall spectrum. The different ingredients of the spectrum are that one is you will see, so these are all basically emission lines I was talking about, okay. At this energies around 1 keV or so, you will see the lines. On top of that, there is a smooth continuum, which is a multi-temperature plasma emission coming from that accretion column. On top of that, around 20 or 30 keV, we are expected to see this reflection hump, which is again reprocessed emission from the hard X-rays. Okay, and we are also expected to see the ion emission line at 6.4 kV as well as the ionized ion, hydrogen-like and helium-like ion from the highest temperature zones. Okay, so these are the ingredients that we are expected to see if we look at the sources with X-ray telescope in this energy range. Okay, so now one of the important things is that this reflection is very poorly understood because the instrument that we have been using to study the sources, they go up to mostly 10 kV, and above 10 kV the sensitivity is very low. So although it is expected to show this feature or the reflection feature, it was not detected so far. Okay, so that is an important point. Okay, so to study these sources, we have mostly used these two observatories called XMM Newton and New Star. XMM Newton, so okay, so the importance is that when you want to look at the sources in a broad energy band, now unfortunately, apart from AstroSat, there are no observatory that observed such a broad, region. So we want simultaneous observation because these are highly variable source. If you observed with one observatory at one time, another observatory with other time, then the characteristics will be different. So you cannot average out those characteristics. So there has to be a requirement of strict simultaneous observations covering a broad energy band. And these are the, just to show you the effective area of different instruments that work in these are the imaging instruments basically. So I'm only showing the imaging instrument. This curve is for New Star. The New Star is the only instrument that actually has a focusing capability all the way up to 80 kilo electron volt, and that is the only observatory available in the sky which can focus X-rays up to 80 kilo electron volt. Earlier observatories like Swift, Suzaku, Chandra, XMM Newton, they go only up to 10 kV or so. Beyond 10 kV, they don't have a capability to focusing the X-rays. And focusing X-ray is very important because we want higher sensitivity. If you can focus the X-rays at small point, you increase the sensitivity. And that is how you detect the different faint features if you increase the sensitivity. So we have selected these two observatories. This is the XMM Newton, the European observatory, and this is New Star, NASA observatory. This was launched almost 10 years ago. New Star, as I told you, has high sensitivity and good effective area at high energies. The XMM Newton has large effective area and very good energy resolution at soft energies. So when you combine these two observatories, you will really get a broadband coverage with very high sensitivity. Okay, so with that goal in mind, actually we have observed again, as Vishwit mentioned in the morning, that we are studying the different individual sources and then try to collectively give some idea about the class of the sources. So we have started with observing three sources. These are intermediate polar category. Okay, so they have the partial accretion disk, and they were observed simultaneously with XMM Newton and Chandra. So I won't go into detail of this data or observations, but the spectra basically shows very beautiful, very nice spectra. So it was for the first time possible to look at the signature of the reflection, as I told you, the reprocessed emission. Earlier it was not possible because of the lack of sensitivity in this region, about 10 kV region. And simultaneously we can also detect the ion line. So this hump corresponds to the presence of the ion emission line. Now this is basically a blend of couple of lines. This instrument doesn't have enough energy resolution to resolve the lines. So we are expected to see here the fluorescence line at 6.4 kV, the hydrogen-like, helium-like lines, and different multiples of the component of these lines also. So it's basically a forest of line in this area. If you have really good instrument, you can resolve all the lines. But here this instrument was mostly designed to do a broadband spectroscopy. So you will see a broad hum only. But this is very important because the ion 6.4 kV fluorescence line has a direct relation with the reflection component. So if you see a 6.4 kV line, then you expect to see the reflection component. But earlier it was not possible. Now we can have both the features together. So this was basically a very important result from the New Star and XMM study of these sources, that for the first time we could detect this reflection hump. No, they are basically kind of same observation. So we have two observations here from two different observatories, but it's I think part of systematic as well as this statistical fluctuation.
How do you calculate
Error bars are, so y-axis is mostly a ratio. Basically, data is flux. Okay, flux versus energy. That's the spectrum. So the flux, whatever energy, photons per centimeter square, Earths per centimeter square per second. So that will have error bar, the measurement error bar.
Oh, so the systematic.
Yes,
Okay.
these are the measurements, right? Right. And when you but over time, this measurement for few, let's say, kiloseconds over a day, let's say. So this is over time. Right. No. Okay, so this is the broadband spectra, overall spectra, which looks like pretty interesting for this source, and we were able to detect almost all the components: the continuum, the iron line emission, the reflection hump, and of course we could also determine the amplitude of the reflection, which is around 0.6, and the strength of the iron line is about 90 electron volt. So all of these components that were expected from these systems, if we have a sensitive resolution, we can actually detect those sources. Okay, so another interesting source, basically, as I told you, are the polars. As I already mentioned that this polars don't show multiple periods because of the phase locking between the secondary star and the white dwarf. But there are some exceptions to this. Okay, this is not a very strict definition. Although they have a strong magnetic field and there is a phase locking between the two stars, there are some exceptions where we see a very small difference between the spin and the orbit. Okay, and there are only handful of such systems known. These four are the well-known system. This is maybe or may not be, which is called asynchronous polar. The polars are usually held to have synchronicity because of the tidal locking. But there are some exceptions, and these are the only four known systems. So typically, when we see this asynchronous rotation, the difference between the spin and orbit is only 1%. Okay, so you can see that the orbital period is 3.36. This is spin period is 3.37. So these are very close. Okay, unlike other systems where the asynchronicity was 90%, these are hardly 1 or 2%. Okay, so these are very interesting systems which we call as a unique polar or asynchronous polar. And we have studied a couple of them. I will just show you one as an example. That is, what happens is that because of this asynchronicity, it's a very small asynchronicity. Okay, so what will happen is that one will rotate slightly slowly, another will rotate slightly faster. So there will be a twisting of magnetic field lines, pole switching, all sort of complexities will be happening. Okay, and when you look at the light curve, basically the count rate versus time. Okay, the intensity of the source as a function of time, and if you try to fold that on a known period, you will see this. This is something called phase folded light curve. Okay, so you will see a lot of dips and peaks in the light curve. This is just because of this small asynchronicity that introduces such a complex behavior in the light curve, and this could represent a, when you plot this light curve, divide this as a function of energy in different energy bands. Let's say this is below 3 keV, this is 3 to 10 keV, and this is 10 to 40 keV. Then you will see a slight difference in the light curve. The amplitude basically changes as a function of energy. So this might indicate that there is some complex absorption system is absorption effect is going on in this system, which is affecting the X-ray emission. And when you take a ratio of these two, you will see something like this. So there is a peak here, which shows that the spectrum at this phase is different compared to spectrum in this phase. Okay, so if you look at the spectrum in two different phases, you will see the effect. Okay, so that's what we did next. Okay, so here this is an example of one of the high resolution spectrum. Okay, you can see the oxygen lines here for the sources. These were obtained from the XMM Newton grating, oxygen 7 and oxygen 8. The other lines are not present. So at least the accretion column has the lowest temperature which can emit the oxygen line. The highest temperature could be very high. So the highest temperature near the shock turns out to be around 43 kilo electron volt. Okay. Now, since this material is under the influence of the gravitational potential of the white dwarf, the temperature of the shock has a direct relation with the mass of the white dwarf. Okay. So mass of the white dwarf is a very fundamental quantity. So in these systems, actually there is a direct measurement of the mass of the white dwarf if we can measure the shock temperature, because the shock is happening because of the gravitational potential of the white dwarf. Okay. So, and that actually we can reliably measure only if we have a broadband spectrum, because the shock is very high temperature. So if you can cover the high energy part, you can measure the shock temperature. And in this system, it turns out that shock temperature is of the order of 40 kilo electron volt, which corresponds to the mass of 0.87 solar mass for this particular white dwarf.
This shock temperature just depends on the mass, or like magnetic field will play some role for polar systems, right?
But close to the surface of the white dwarf, it is mostly governed by the gravitational potential of the white dwarf. Magnetic field will just guide it. Shock happens because of the velocity transition.
Yeah.
Correct. So that, and that velocity is attained by the gravitational potential of the white dwarf, gravitational pull of the white dwarf.
Okay.
So there will be some effect definitely for the magnetic field.
Yeah, I mean, what I'm saying is like if this relation, like temperature with the mass of the compact object, is cannot be followed for polar system as well as like non-magnetic systems.
Correct. So
like,
that has to be there. This is under some certain assumptions that if you can kind of little bit ignore the effect of magnetic field, where there is a less magnetic field in IPs. Basically, in IPs you can attend this.
Okay, so this whatever temperature has been correlated to the mass of the white dwarf is only done for the IPs systems.
For the systems which has a lower magnetic field, where you can actually ignore this effect of magnetic field. Otherwise, you will have to do full MST simulations and include the effect of magnetic field. Okay, so then this is the spectrum that I was talking about. So if you take the spectra at two different phases, you can see this difference. Okay, so there is a clear absorption effect taking place as a function of spin. So as the white dwarf rotates, some absorbing material comes in between the observer and the X-ray emitting region, which is absorbing the spectrum. So that is what.
Just a quick question. Just this, what is the amount of mass that's accreted compared to the size of the mass of the white dwarf over some significant period of observation?
The amount basically depends, on the secondary star. It's basically mostly a main sequence Roshilov filling star.
But it's not like it's doubling mass or something, right?
No.
Really small fraction.
No. It's of the order of 10 power minus, I think, 7 or 8 grams, something like that. Oh.
Can exceed the Chandrasekhar mass limit and eventually will cause collapse. That can happen. Need not necessarily be in a given system, but
correct. So these are kind of progenitors for type 1a supernova. That time scale is actually very kind of large, whatever we're talking about. So in fact, because of that reason, these are pretty good sources for type 1a supernova. Some of the white dwarf can explode as a type 1a supernova. It is basically going on the forever until some kind of explosion disrupts this system. As long as there is a binary system and the secondary star is filling its Roshilov, that accretion is going on. Okay, so I think I will slightly rush through. This is again something second system which is very similar to the previous system. Again, here we have seen the oxygen line. Oxygen 8 is not there, but oxygen 7 is there, and this is the expected location for the nitrogen line. So this is again from the XM Newton reflection grating instruments. So if we could have detect some other lines, we can say that what is the different multi-temperature zone of the accretion column. Okay, and this is again a spectrum. Here the highest temperature turns out to be around 32 kilo electron volt, which corresponds to the mass of 0.74 for this particular system. And there is the presence of complex intrinsic absorption in the system, whether this could be due to accretion curtain or accretion stream or it could be due to the accretion disk interaction or the stream magnetospheric interaction. It's kind of difficult to pinpoint at this point. And we didn't know, in this system, we didn't see any reflection component. There could be a weak reflection component, but there is no strong reflection. Okay.
Comes from any Doppler effect. Why is that way?
So here, that's what, here it is kind of difficult to say, because whatever we see here is the limitation of instrument resolution. So we are supposed to see 3 lines over there, but we see one particular hump because of the instrument cannot resolve this line. You can see slightly here there are some 3 humps in the XOM neutron spectra, but that's also limited by the resolution. If we have some kind of nova where the gas is moving out and we can detect the lines, I will show you one example where we have detected the lines. There actually can be because of the velocity of the material. So if you can measure the width of the line, you can estimate how fast it is moving. Okay, so then these are non-magnetic CVs. I think I'll just go directly to the system that we have studied. So here, as you can see here, the white dwarf accretion disk actually extends all the way up to the, practically up to the surface of the white dwarf, because there is no magnetic field to disturb the accretion disk. And this is the region which emits the X-rays. Okay. And one particular system that I was talking about, which is called a dwarf nova, SS Cygni, which periodically goes into the outburst, and this is the optical light curve of that particular system. So as you can see that there is an outburst, then there is a quiescence, again there is an outburst, then quiescence. So if you look at the difference between these 2 peaks, it's roughly about 50 days. So every 50 days or so, this system goes into the outburst, in the optical outburst, not in X-ray. And this people, AAVSO, regularly monitors this through the optical telescope. It's amateur astronomer variable star observer. So they keep monitoring this kind of interesting sources, because for actual observatory, it's difficult to get the time to monitor one particular system for so long. So this guy does pretty good job. Okay. And we have taken the X-ray observation at these 2 points. One, this is called a quiescence state, and this is called outburst state. So there is one X-ray observation here, one X-ray observation here. We just wanted to study that what happens to the X-rays when it goes into the quiescence and the outburst state. Okay. So as you can see here, so here this one actually has pretty good spectrum. This is a high resolution grating spectrum for the quiescence, and this is for the outburst state. So you can actually detect all the lines. I mean, this is the location for neon line, then iron L-shell emission line, oxygen lines, nitrogen line. Same way here, carbon, nitrogen, oxygen. These are all L-shell emission lines. So you can see a lot of lines in this system, which actually indicates that the accretion column, which we are looking at, has a multi-temperature zone. Okay. So, and here, as Prabhu was saying, see, this is the quiescence spectrum. So if you can look at this particular line, this is quite narrow compared to the same line here in the outburst, which has a width. Okay. So here the width actually corresponds to the velocity of the material. If you can measure the width, you can actually estimate the velocity of the material during the outburst. Okay. So these are like some issues that we would like to address for the CVs. Of course, we need to increase the sample size. Asynchronous polars requires further investigation. These are pretty good, interesting sources. And there are several unanswered questions that what happens to the base of the post-shock region? How does the accreting material diffuses on the surface of the white dwarf? We still don't know. Okay. Disk magnetospheric interaction in IPs is an interesting site to explore. Then we have to see bright non-magnetic CVs also and increase the sample for that. Currently, as I told you, AstroSat is kind of ideal instrument because it covers broad energy range. And there are several CVs has been observed, but unfortunately not in a broad energy range. SXT has observed quite a few CVs. And okay, so it's a very important laboratory to study the accretion column, shock, instabilities, and emission from the post-shock region. So I think this is what I wanted to convey about the CV part. In next 5 minutes or so, I will quickly go through the experiments activities. This was all the observational part which I was doing with my students. And in the morning, as Vishwajit mentioned, for X-ray lab, currently the main focus is to develop the polix, and this is what is I'm thinking about after post-polic activities. So mostly the X-ray lab will be engaged with this will one of the significant activity to develop the optics for the X-rays. So the main goal or the purpose of this is just to focus the X-rays. Okay, but when it comes to the focusing high energy radiation, it's very challenging. Unlike when we have this optical telescopes which are using normal incidence and focuses and makes the image, but when you increase the energy of the radiation, the focusing of that particular radiation is very, very difficult. And if we can achieve that, then we can actually have a very high sensitivity observations for these sources, because once you focus the X-rays into a very small spot, and then you can put a suitable detector on that spot, which will be very tiny, very small. So for satellite experiments, this is very important, because then you will reduce the weight of the instrument and it's easy to carry on the space. Okay, so once you reduce that detector size, you will reduce the corresponding background also. Okay, so your signal to noise ratio will increase and the sensitivity will also increase. Okay, so as I told you that I will just give you a very quickly brief idea that how to focus the high energy radiations. Okay, so if you have a typical optical visible light, you put a parabolic mirror, there is a parallel ray of light falling on the mirror, and then it will focus the visible light at the focus of the optics, and you will detect it here. Okay, now if you simply replace this visible light with high energy radiations X-rays, because it has a very small wavelength, it will either interact and get absorbed in the material of the mirror, or it will pass through if the mirror is thin enough. So it's very difficult to reflect and get it focused, the high energy X-rays. Okay, so instead of this region of the parabolic mirror, people use this region for the grazing incidence. Okay, because the normal incident won't work for the high energy radiations. So something called the Bragg reflection, the grazing incidence works. So if you use this part of your parabolic mirror and your incident angle is very small for the X-rays, then it will just graze it and get deflected and get focused. Okay, so then your mirror will have to have a very shiny smooth surface in order to reflect the X-rays. Okay, so what will happen is that if you use this method, then you can actually reflect the X-rays. This is total external reflection will happen. It will get focused here. Now in X-ray astronomy, basically we are always looking for more and more photons. Okay, so if you have just one small mirror and try to make a telescope with that, you won't collect many more photons. So your signal to noise ratio will be poor. So you need to increase the number of mirrors. Okay, so how do you do that? You cut out this portion which is not going to use, okay, and then you have this part of the parabolic. You make a lot of parabolic mirrors and then stack them together. Okay, so the X-rays will fall on each of the mirror and then will get focused here. Now it has been shown by various groups around the world that X-rays, if you want to focus it without any aberration effects, they have to bounce through two mirrors. So it has to be parabolic and hyperbolic mirrors, and it looks like something like this. Okay, so this section is this is paraboloid, this is hyperboloid sections. The X-rays will fall here. The inner surface of this mirror is coated with very smooth material like gold, iridium, or platinum, and it will be falling at a very small angle, and then this mirror will have a focal length. For example, here the focal length is 10 meter. So at 10 meter distance, if you put a detector, it will get detected. Okay, so this is how, this is one of the image for the Chandra Observatory, which was launched by NASA. And yes, Prabhu. So that actually depends on from observatory to observatory. Here I am showing the picture for Chandra Observatory, which uses only 4 mirrors. I think the outermost diameter is about 1 meter or so. Oh. Sorry? Which axis? Oh, here. This diameter, right, you are talking about? Oh, these, I'm not sure for the Chandra how long are the mirror, But for other observatories like NuStar and XMM, they are about 200 mm, so 20 centimeter one portion and 20 centimeter other portion. Which one? Okay. So here it is 0.8 meter. For so here what will happen is that if you can somehow manage to make a perfect hyperbola paraboloid, then it will be efficient reflection of X-rays and you will get a very nice image. So far the Chandra has the best angular resolution of the order of sub-arc second, okay, because they are using a perfect hyperbola and parabola. But if you try to do that, then you have to restrict the number of mirrors, because in order to maintain that shape, the thickness has to be more. If you have more thickness, then number of numbers will get reduced. So Chandra only uses 4 mirrors, and that will affect your collecting area. Collecting area will be smaller.
Yeah, if you use this Bragg reflection in order to focus, then it works only for a particular wavelength, right? So when you want to look at the spectrum, what do you do?
No, it will work for all the wavelengths. Basically, what will happen is that.
But the reflection condition changes for the wavelength.
See, it's basically parallel beam of X-rays coming from the celestial object, and where you're pointing your instrument towards that, its X-rays are coming at various angles. Okay, so here it's only that for effective reflection, the angle will be of the order of degree or less. But if you have coatings, so that coating of the inner material also actually decides that what energy you can reflect. Okay, if you have a single coating, then it effectively works up to only low energy soft X-rays. If you use multi-layer coatings with high Z and low Z materials,
So
then
you have layers of different
materials to extend the energy range of the reflection.
Okay, thanks.
Here actually, I mean, this won't affect any polarization. This is mostly, I mean, see, this is a versatile instrument. This people have been using so far for the spectroscopic observations. Okay, so then people have studied different material, and the important parameters here are basically the energy of the photon and at which angle it gets reflected. Okay, so if you see that, if you have a photon coming at an angle of 2 degree, only up to 2 keV it can be reflected efficiently. But if the photon comes of the less than 1 degree, it can go all the way up to 8 keV or 10 keV reflection. So if you have a single coating of 300 angstrom with iridium material, then this is what can happen. Similarly, if you have again, this is basically same plot. It shows the angle. If you have a less angle, the reflectivity is much better. Okay, so the photon has to reflect at very, very small angles. Okay, so I will quickly run through these things. These are some actual pictures that this is the NuStar telescope that has used this multi-layer coatings, high Z and low Z material, and that is why I'm saying that the NuStar is the only observatory that can extend the focusing capability up to 80 keV. Before, people were using only single layer of coating, and it can reflect X-rays only up to 10 keV or 8 keV or so. Okay, so there are different steps. Here, the focal length of the NuStar is about 10 meter. Okay, the number of cells it uses is 133. So Chandra has only 4 mirrors. NuStar has 133 cells. So effective area will be more. And they use this high Z low Z material, so the reflection of different energy photons can be possible. And at the end, this is how it looks like. Okay, when you have X-ray telescope, you can make one particular shell. Inside that shell, another shell, another shell, another shell to increase the effective area. So it all depends that how well you can actually align. The only requirement here is that all of this mirror has to be confocal and coaxis. The axis should be same. They should focus the X-rays at one point. That is the only requirement for all of these mirrors. Okay, and that is actually very, very difficult, because there are thousands of pieces here. You have to align all thousands of pieces in such a way that all of them focus X-rays into one point, one small point. Okay, so that is why it is technologically very challenging part to develop the hard X-rays photons. Okay, so these are the process. Sorry.
this grace angle, like I guess that is required to handle different energies, because high energy ones probably require like a smaller grace angle.
Actually, high energy one will require a very small angle. So as the energy increases, the grazing angle decreases.
Now that grace angle will also determine like where the detector will be placed, right? Because if your grazing angle is very small,
so
then size you need to put detector at a longer distance.
Correct. So that is why the thing is that the reflecting the hard energy X-rays is very, very difficult. Only NuStar could do it because the focal length is of the order of 10 meter. Okay, so there is a telescope of 10 meter which you have to send in a space. So it's very difficult thing. So what NuStar actually did is very clever thing. It was kind of very compact at the beginning. They put some extendable mast to achieve this 10 meter. Okay, so it was very compact thing. When it went in the space, then it slowly unfolded and achieved the 10 meter focal length.
So that size limitation is there
size
also, like
it's always
for high energy
just
detection.
like any other optics, this will have a focal length. Yeah.
Thanks.
Okay. Okay, so these are all kind of technical details basically. This project is, as you can see, that it's very technologically challenging project, and it will be done in collaboration with Pan India, so PRL, ISRO, and RRI. Mostly at RRI, we will be actually dealing with the assembly of the mirrors. So as I told you, there will be thousands of mirrors, and we have to assemble them very precisely, so that we can have a very nice focusing spot. So RRI will be involved with that particular steps. Okay, so this is how the final looks like. You can see all the mirrors here. They are actually separated by about less than 2 millimeter. Okay, and these mirrors are made up of glass sheets. So you start with a glass sheet. Okay, then give it a thermal treatment to give the curvature. Then you coat the inner surface of the glass sheet with multi-layer coating, and then you assemble it to make this entire this shell. These are some science results, so I'll just skip that. We have in India, Astrosat has already used X-ray telescope, which works in the soft X-ray part. So it's called a soft X-ray telescope. Here, there as you can see, the Astrosat has used aluminum foils instead of glass. There is very thin aluminum foils, and they coat aluminum foil with the gold material. So here there is only single material. There is a gold material. So it can go only up to 8 kV or 10 kV. It cannot go to hard X-rays. Okay. So this is how the this 320 concentric gold coated mirror looks like. So this was how it was assembled in the SXT, and there is a CCD placed at the focal plane. About I think 2 to 3 meter was the focal length, and so there has been a heritage in India to develop this soft X-ray telescope. Now it's naturally to go beyond this and develop the hard X-ray telescopes. So we will be kind of involved in that project. Okay. I think we have this project is pretty initial stage at this point, because as I told you, this will be mostly taken up post Polix, and there is a collaboration with PRL, ISRO, and all of this. We have submitted a proposal to ISRO. There is a positive response from them. So we will be starting some initial designs and exploring various techniques to assemble the mirrors. Okay, so I think I'll just show one last slide. So for hard X-ray optics, a suitable reflectant coating material to enhance the reflectivity at higher energy is required. Okay, and people or the groups around the world have done this kind of research. So there is a nice, so people use this gold, platinum, silicon, carbon, or tungsten. These are the usual used materials. Okay. And recently there has been study that if you use material called nickel vanadium, it can extend the focusing capability all the way up to 150 instead of 80 keV. So we can actually go all the way up to more than 150 or so. So this is one of the promising material that we can use in future. And of course, it has to be lightweight, smooth substrate. Smooth in the sense that the X-rays has very small wavelength. If there is a waviness or the surface of the mirror is not smooth, it will get scattered instead of reflection. Okay, so it has to be very smooth at the level of the wavelength of the X-rays. So that's the another challenging part. And we have to use a good detectors at the focal point. So currently people are using some solid state detectors, cadmium zinc telluride or cadmium telluride, or silicon trip detectors. These are the detectors which are pretty compact and small detectors with very good efficiency. And we have proposed this as a technology development program based on the heritage from the AstroSat SXT, and has obtained a very positive response from PISRO. So I think I'll stop here.
Any question?
Sure.
How different it is going to be in terms of, like X-ray polarimeter also actually picks up the signal. So supposing you use that itself for looking at this. So how would you compare it with
X-ray polarimeter? So as I told you, like this is a versatile thing. We can use this to study the polarization of the X-ray also. The only thing is that when we look at the Polix has basically non-imaging instrument. Okay, so there will be slight sensitivity difference. If we use the optics and focus the X-rays, then the detectors will be smaller, so we can improve the sensitivity. But I think IXP is using optics, right, Paul? Yeah, so up to 8 kb, right?
I mean, using glass, isn't that very heavy?
No, so these are very thin glasses. It's a 0.2 mm thin. Okay, so it's a very thin sheet of glass. Basically, the glass that we use in the screens, like very thin, so thin glasses. Then we give a treatment, but so SXT was using aluminum, so that was heavier compared to glass.
Oh, okay. I would have thought.
But it is very fragile also. You have to handle it very carefully, otherwise it will break.
And that's already constructed.
Constructed, yes, yes.
So for this wavelength range, like you don't need perfect focus, right? As long as the focus covers the detector, that is enough.
Correct,
right?
correct.
Basically, so you're not forming an image. You're only collecting all the photons.
But that can actually, if the detector has a capability, because it's a pixelated detector, we can form the image also. We want the image.
You want the image. Then you need perfect focus.
Right.
Yeah. Okay. So if you only want to do spectroscopy, then you don't care, like if it's.
Yeah. So so I was talking to promote the. So all these reflections you are talking about, like grazing angle and all, these are like Bragg reflection.
These
right?
are mostly Bragg. Total external reflection.
Yeah.
Mostly.
So now, is there a problem of having higher order reflection peaks? Because Bragg, like you get also like for n is equal to 1, 2, and so on. So is how do you handle like, or those are not significant? Because you have this condition 2D sin theta is equal to L lambda.
That is true.
So n is equal to 1 will be the dominant.
Correct.
2D sin theta is equal to lambda. But other values of n, does it matter?
I'm not 100% sure, but most likely they are not so significant at this range.
Okay.
Okay. I'm not sure about that. Maybe you can check it out.
No, but angle. Yeah. No, because if the reflection angle varies slightly, then. Yeah.
Coatings are mostly you do with the sputtering machine. You have the not really crystal. It's basically earlier people used to do evaporation.
Yeah. No. X-ray, the range of wavelengths, like whatever coating you put is like almost atomic size, right? Like is the medium, can you consider
The smoothness is of the order of wavelength of the X-ray. So it's basically angstrom level.
Exactly. So that is the thing. So because usually mirror
Huh.
the whatever the smoothness is compared to optics, it is much smaller than the that wavelength of like optical wavelength. But here
Compared to optical wavelength, it is much smaller, but here it is compared to X-ray wavelength.
So that's why like this diffraction kind of thing can come actually.
Okay.
It sees some not a continuous structure.
Uh-huh.
So that's one thing.
Okay, maybe I think we can check it out there.